morning, dear friends. Today is the session for Man Ki Baat. And you know, we have been discussing about range, endurance, gliding flight, then turning flight or accelerated flight. There is a pull-up, there is a turn. That is primarily the topic what we covered in the last module. And when I was getting tired giving lectures, recording lectures after lectures, and we hardly get some feedback from the blog. My TA will tell these are the basic questions they have in the mind, they are settling among themselves. It's very heartening that you are participating, you are discussing, and we are watching that, okay? And that is how I pick a few points. What should be the Man Ki Baat topic? One of the most important things which I need to mention here, please understand, whatever power required, thrust required, range, endurance we have discussed them in a standard atmosphere. That is, we have not assumed any wind blowing. That is, suppose the aircraft is going like this, in actual atmosphere there could be wind following the aircraft, there could be wind from just opposite direction of the motion of the airplane. So if the airplane is going like this, if wind is coming like this, the atmospheric wind, okay? Then we say it's a headwind. The aircraft is experiencing headwind. If the aircraft is going this direction and atmospheric wind is coming in this direction, then we call it tailwind. In fact, there will be atmospheric wind at any altitude. Some altitude is more, some altitude is less. And they will have their own direction, right? And generally we define that direction in terms of north, south, east and west. However, if I know what is the direction of the wind, which is atmospheric wind, then I can always resolve those components along the aircraft x-axis and one perpendicular to that. So you can easily find out whether it is a headwind, whether it is a tailwind, whether it is a crosswind. Crosswind means the aircraft is going like this, wind is coming like this, perpendicularly, from right to left or left to right, okay? That is how we characterize. What is important to understand here, whenever we have talked about power required, thrust required, or range or endurance, we have always spoken in terms of an atmosphere, standard atmosphere, where there are no atmospheric wind. That means I can assume that the atmosphere is stationary. That is why whatever air relative velocity of the aircraft was, that is exactly same as the ground relative speed. Okay? Because the atmosphere we assume to be having no speed, no velocity. Typical standard atmosphere. But we will quickly see if there is a headwind or tailwind, what will happen. Okay? And in the formulation, fundamentally where we should be careful. Right? So today this Man Ki Baat, one of the topics I have chosen is to give you a guideline how to handle atmospheric wind, where it will affect, where it should not affect. This is one part. Second, we will be talking, and I perhaps might have mentioned about a delta wing or a wing of this sort of a shape, which is also called flying wing. And today also you will see that I will take you to our one of the very important room where we actually make models which are not aero models, which are actually designed on the blackboard, then it is fabricated. And that is the fun. So one clip will be there where you see so many delta wings are lying, so many other type of configurations lying, the room is flooded with so many instruments, and the whole truth that finally we have been successful in designing a low altitude, long endurance, unmanned aerial vehicle, autonomous, which you might have seen in the newspaper, and a lot of demand on us to meet the requirement of so many agencies. That also we are showing you from classroom what we have understood. We have gone to a room where we can experiment. Once we are sure through initial flight these design parameters are okay, Because in that model, we also instrument it. We put the accelerometer, we put angle of attack sensor. For example, if you see this model, delta wing, here we have installed angle of attack sensor and beta sensor. The angle of attack sensor will be horizontal like this. It will measure angle of attack and beta. Sometimes what we do for symmetry, we put beta sensor, side slip angle or yaw angle sensor here, and angle of attack sensor here, so that there is a symmetry. Symmetry is not lost. We put IMU, inertial measurement unit, inside this, which is gyro based, which tells you the attitude, accelerations, and the orientation through a magnetometer based instrument. Okay, these are extremely important. It's not a matter of what you fly. Any area I can fly. George Kelly has told us that you have to give sufficient speed or velocity. But what is important for a designer is whether I am able to fly the machine the way I have designed the mission requirement. Right? For example, I want it should attain a height within this much of time, whether this model is doing or not. If I want it should turn at this particular rate, whether this model is doing or not. That is what is important. That is how we get hands-on experience on what are the problems, how one has to sweat to convert do how to know how, or know how to do how. It's a reversible process. Sometimes you know something theoretically, then you try to implement it in hardware, and when you implement, you realize, oh, somewhere I am doing mistake, come back. So this sort of a iteration goes on, and finally you find, which you will be seeing, and clip you must be watching now on our unmanned aerial vehicle. Okay, that's a grand success story of us, the student ourselves, and one of the few startup members who joined us. So that is also one of the aspects you will see.
Welcome to the Flight Laboratory IIT Kanpur. I am Vijay Shankar Divedi, student and TA in this course. This is the place where we fabricate our designs. Here you can see I am surrounded by a lot of instruments and equipments which are required to make initial design of an aircraft. You can also see many airplane models which we have developed to meet some specific requirements. This is the flat plate which was developed to compare the aerodynamic characteristics with the flying wing. The flying wing and two more other configuration of the flying wing. Glider which has very good gliding ratio, about 45. This is the powered parafoil. The parafoil attached to the track. Here are cells and it fills with air, and its cross section takes the shape of an airfoil, and this is attached to the suspensions. When the suspensions are pulled in a symmetrical manner, the camber changes and it works as an elevator, and at the same time if we increase our throttle, it climbs. For the steering, the suspensions are pulled in a differential manner. And now this is our state of art low altitude, high endurance unmanned aerial vehicle which is fully autonomous. This is fabricated with glass fiber, carbon fiber and other sandwich materials. It has wingspan of 3.3 meters. For tail we have three options. The one you are seeing here is inverted C tail. The maximum takeoff weight is 25 kilograms. It can carry payload up to 5 kilograms, which can be increased by decreasing the fuel weight. Currently, as a payload, a high resolution camera is mounted which can be operated from the ground station. The required takeoff distance is 50 to 100 meters depending upon runway and runway location. Its climb rate at sea level is 2.5 meter per second. The operational altitude is 5,000 feet from the takeoff point. Its endurance is 6 to 8 hours, which is remarkable in itself. It has operational range up to 100 kilometers from the ground station. The best part of this place is these facilities are not limited for the IIT Kanpur students only. Any student or researcher from anywhere in India can take advantage of these. If you want to use these facilities, simply mail to us. We are available all the year. However, it is preferable in October and November. Thank you.
I come back to the effect of atmospheric wind primarily in this session. Remember, when we are calculating range, what was our understanding? That we said ds, small distance traveled, is v, with a constant speed it is going, into dt for the small duration time. But what is this? This is distance. This is distance. Which distance? How do you measure the distance? I measure it with respect to the ground. Okay? So this is actually, when I am thinking of ds, it is vg dot dt. Since so far we assume that there are no atmospheric wind, so air relative speed of the vehicle or the ground relative speed of the vehicle were same, right? But now the moment you say there is an atmospheric wind, that is, suppose this is the airplane, and see the wind may follow the tail like this. This is called tailwind. And there could be a case where wind is approaching the aircraft like this. This is called headwind. So this was not incorporated because we are all working in standard atmosphere, where we assume that the atmosphere is still. There is no atmospheric wind. So what is the implication? Implication is very simple, that I can write air relative speed minus VW will be the. So what is the difference? Difference is, if this is the atmosphere, say this is atmosphere, this is the ground, and this is the vehicle. The vehicle has a speed with respect to the ground, which I say Vg. The atmosphere is also having a speed now, or velocity, because there is atmospheric wind. I say Vw. So then what is the speed of this aircraft with relative to the air, medium, or the atmosphere? That is the question. That is responsible for giving lift and drag, isn't it? Since Vw is also a reference to the ground and Vg is also a reference to the ground, I can easily write Vg minus Vw will be air relative speed of the vehicle. This is air relative speed. There is no doubt. So what is Vg? So Vg is actually is V plus Vw. Correct? So when I again come back to this equation, ds equal to V into dt, and I know that V has to be V ground, or V with respect to the ground, and it was equal to the air relative speed when there were no atmospheric wind. But now if there is atmospheric wind, I have to write ds as Vg dot dt. This is the correction. Correction means this is the, you have to modify your thing, where Vg is V plus Vw. This is clear? Okay, this is at a fundamental level. Now, we again go back to our formulation of power required. Let's see where we have to modify if there is an atmospheric wind. How did we calculate power required? We said power required is nothing but thrust required into V. Which V? Something is to be moved, some work has to be done. Unless there is a displacement, there is no work done. And the rate of change of that work done is power. So this V has to be V with respect to the ground, Vg. Is it clear? The vehicle is moving with respect to the ground. Now the question is, when there were no atmospheric wind, then Vg and air relative speed V were same, so we calculated like this for standard atmosphere. Very fine, because standard atmosphere, there is no atmospheric wind. But now atmospheric wind is there, so what happens? PR is what? Thrust required into Vg is Vw plus V. where v is the air relative speed from this. Just to give you more insight about v relative, air relative speed, imagine, first of all, we understand that the lift and drag, they are generated because of relative airspeed, right? So even if theoretically aircraft is stationary, if I have atmospheric wind coming like this, so there is a air relative speed. So it should produce lift and it should produce drag depending upon what is the orientation. So theoretically it's possible. The airplane is not having any motion with respect to the ground, but still because of atmospheric wind there is a lift and that is sufficient enough to balance the weight. Theoretically it is possible. So in that case, what is the power consumed? Nothing, because there are no motion of the airplane with respect to the ground. So when you are doing formulation with wind, atmospheric wind, we have to be careful that here it should be Vg, and Vg you know is V plus Vw. Okay? Now let us revisit this range, let's say propeller driven range. Because range estimation formulation uses Vg, that is speed with respect to the ground. For endurance, nothing, it's air relative speed, so fine, no issues. Now see, if we come to the range, what I see, range is maximum when CL by CD is maximum. Correct? So there is a corresponding speed for that, corresponding air relative speed for that. But if there is atmospheric wind, how should I change this formulation? Right? That is the question. See, range maximum, from that I am finding it is when CL by CD is maximum. This was propeller driven IC engine aircraft. Now let us go a little bit into it. If this is power required versus speed, let's say it is something like this. You are now aware. Now watch out. This power required is proportional to CL3 by 2 by CD. You can check your notes. And V is proportional to 1 by CL to the power half, because V is under root 2W by S rho CL. So if I divide CL3 by 2 by CD divided by CL to the power half, what I get? I get CL by CD. Typically I am talking through these dimensions, these variations. So what is the interpretation is, if I draw a line which is tangent to this power required versus V, and the tangent starts from V equal to 0, this point is basically, which we have done, V for CL by CD maximum, because the slope is giving CL by CD. Okay? From this ratio I have tried to explain, but also you understand what is this slope? This slope is PR by V, that is thrust required, and you know thrust required is proportional to CL by CD. I have tried to interpret this slope through CL3 by 2 by CD and CL to the power half, and I have shown that this is nothing but CL by CD. Now try to see, what is this slope actually for us? This slope is nothing but PR by V. PR by V is nothing but thrust required, and this is the minimum slope. Any other line if you draw, we have seen that the slope will increase. So this is the velocity at which PR by V is minimum, or thrust required is minimum, which implies CL by CD is maximum. So this is the V max for CL by CD max. Right? I repeat, this is the point where this slope PR by V is minimum, that is thrust required minimum, and that thrust required minimum means you have to fly at CL by CD maximum. That you know, thrust required is W CL by CD. If thrust required is minimum, you know CL by CD has to be maximum. So from this slope also you get a interpretation that this is the velocity where if I fly, I will be flying at CL by CD maximum. Okay? And that will correspond to, from here, CL by CD maximum means I will get range maximum. Now the question comes, what happens if there is a wind? That is the question we are trying to address. So there is a very simpler way also there to interpret. If I draw, let's say no atmospheric wind, okay, PR, and this is V. I know this is the power required versus velocity, and when I draw this tangent and the slope is TR equal to PR by V. So this is the speed or velocity at which thrust required is minimum, and you know thrust required equal to W by CL by CD. So this implies CL by CD maximum. So this gives you V for CL by CD maximum. And the moment I say it's V for CL by CD maximum, I know this is also the speed for a propeller-driven aircraft for which range is also maximum. That is, this is also the V for range maximum. This is when we talk about no wind condition. But what we are trying to discuss today in our Man Ki Baat session is what happens if there is a wind. So now we are smart, we know for our wind case, that is atmospheric wind case, no more you are assuming the atmosphere is stationary, then you know Vg is nothing but Vw plus V, where V is the air relative speed and your power required is thrust required into V plus Vw. Okay? So in this case, thrust required is power required divided by V plus Vw. And now this TR, which is PR by V plus Vw, has to be minimum so that the CL by CD will be maximum and hence range will be maximum. Is the statement clear? Now it is V plus Vw. So now in this case, the thrust required should be minimum, and thrust required minimum means CL by CD is maximum, and CL by CD maximum means the range is maximum. So how do I use same graph? What I do, this is power required versus V. Now suppose if it is a tailwind, as per the convention, if this is an aircraft, this is X, this is Y, this is Z. Tailwind means like this, that is along TW is tailwind, along X direction, and HW is headwind, the opposite direction. So as far as this convention, tailwind is positive. So what we will do, if it is positive means the power required has to be divided by a number larger than V relative, which is in stationary air. It was. Earlier we were doing that. So very simple, if this power required versus V graph is available with us, what I will do, I also further understand what is power required is thrust required into air relative speed V. Which V? This is Vg. Okay? That is how this thrust required has come. The same thing here, which I have written in other notation. So now since there is a Vw, what I will do, if it is a tailwind, that means this is positive, tailwind, this is positive, let's say 5 meter per second or 10 meter per second tailwind is there. So what I will do, I will come to this x-axis and cut 10 here in the negative side. And then I will draw the slope from here. Okay? And for zero wind, slope was drawn from here. This is for tailwind. Now you could see the power required divided by whatever V from here, plus this of much of tailwind has come. So you will get different speed. And suppose if it is a headwind, then you take here, let's say 10 meter, you cut 10, and then you try to find out the slope. Though it is indistinguishable in the scale of this diagram, but you can guess one thing, that as I am going off from no wind condition, the slope of this line is reducing. As I am going towards headwind, slope is increasing. Correct? What is the meaning of that? Let me draw a better diagram so that you understand. If it is like this, let's say this is your no wind, and let's say here actually there will be if you see very carefully, there are 3 points. One is definitely there is a no wind, so this is the V for no wind NW. As there is a tailwind, the slope changes, and this speed is less than the speed for no wind. That is speed for CL by CD max with a tailwind, it will be less than V NW. And with the headwind, this V for CL by CD max with headwind will be more than V no wind case. This is graphically you could see that because this is power required and speed. Okay. So what is the message? Message is simple. If I am going from here to here at that point, and suppose I am going like this, there is no atmospheric wind. Let's say it takes some 50 minutes. Now, second time when I am traveling from Kanpur to Lucknow, let's say Kanpur and Lucknow, then again when I am traveling, I find there is a tailwind. What will happen? The moment there is a tailwind, the air relative speed will reduce, isn't it? As it reduces, because we are talking about air relative speed with respect to the atmosphere. That is reducing, so lift will reduce, so you have to increase the ground speed. Okay? To ensure that you have got same air relative speed to balance the lift. In the process, what will happen? You will reach Lucknow faster. Right? In a contrast, if you see, when I am going from Kanpur to Lucknow, there is a headwind. What this headwind will do? Since there is a headwind, I need lesser ground relative speed to have the same air relative speed to have the lift, because lift depends upon air relative speed. So my ground speed will reduce, so I have to take longer time. I may even lose the trajectory, I may even lift up. So what is done? You have to go little faster. So we give a throttle, but if I only increase the ground relative speed, then air relative speed will increase, so it will lift up like this. So we nose down the aircraft, we reduce the angle of attack and try to compensate for time. That's all. Okay? But if I am a passenger, I will always love to have a tailwind so that I can go faster and reach earlier. Okay? So this is one of the concepts I thought I must discuss with you. Now, natural second question will come: what happens to the jet engine aircraft? Air range, if you see, it is 2 under root 2 by rho s, 1 by CT, CL half by CD, W naught half minus W1 half. Here you see the range is maximum for other condition remaining same if CL half by CD is maximum. Okay? Again the same situation will arise that this is for no wind condition. Okay? I am leaving a question for you. How will you handle VW, presence of atmospheric wind, and give a graphical solution as we have done for range in case of propeller driven aircraft. Because I just give you a hint, when you start thinking like this, you will know that ds is nothing but v dot dt, but now as there is an atmospheric wind, I have to be more careful. I write vg, speed respect to the ground, dot dt, and vg is nothing but v air relative, so vw dt. This should be kept in mind to find out what is the effect on range and how do I interpret CL half by CD and its corresponding speed. What is the speed I should fly to have range maximum? Okay? I hope you will be able to answer this. Let's see. If you get an answer, fine. We are watching your blog. If you don't get an answer, we'll come back in next Mann Ki Baat.